parameterization, or just we can retrieve the parameter. Framework called the Cardinal for saving the non-sorted data into the Darling model. So Cardinal basically use the to simulate non-surface observation and estimate the parameter distributions. So as a result, it generates its essential ecosystems properties. For example, in this case, we just show this NEE from this Kalman simulation results. Also, it generates the uncertainty as well. So for each grid box, we have some the percentile distribution for the NEE results. Another thing that for the Kalman model is that it treats each grid box independently. Obviously, it's quite efficient for this non-data simulation. However, it's not good for the atmospheric data because you know the CO2 concentration not only comes from the local emission contribution, also comes from the transport. So as a result, so we just suggested the two-step schedule. So we call this sequential Monte Carlo data simulation scheme just applied to this problem. The fourth stage basically is the Kalman. So we just use the line observations to constrain this parameter distribution. As a result, we get less spread parameters for this biosphere model direct. Then on next stage, we just bring the GeoScan in. So for the direct the model distribution, so we drive this biosphere model, generates the NEE, and then the NEE drive the GeoScan, so we can simulate the atmosphere concentration and compare to the observation. Then we get further refine of this parameter distributions. However, the problem, as I mentioned before, currently the curve chain is not so work well. So we are just introduce a last stage. We do resampling. Hopefully, we can further filter, and this least important parameters. Okay. So let's slide. We just told current implementation. Basically, we already built this direct module into our full model. We also, because we do a large number of the full simulations, so we also introduce the perturbation table to faster calculation. To some extent, this the full model is ready. You cannot use it to the simulation-based inversion. But for how to do sampling, we'll explore resampling things, but do different ideas. So that's the simple summary. Just what I want to do, just incorporate a more simple model in GeoScan, and while exploring different sequential data simulation schemes. Thank you.
Ultimately, your optimized model will be able to better describe the relationship, for example, between the environmental driver, like air temperature, between the CO2 fluxes.
Yes, because for this one, yeah, we can't. Okay. So basically, we must still separate the different drivers. For example, the temperature or work vapor. For example, we just show this which parameter is dominant for this CO2 concentration. Okay.
So just to be clear, this land cover model takes atmospheric observations of CO2 fluxes derived from atmospheric satellites, is that right?
No.
It uses some kind of land cover model.
Yeah, basically, so you can do like this way. You get fluxes, then assimilate this flux into the biosphere model. But that way is not perfect. You have many questions because the flux actually correlated with each other. So you cannot treat this information as independent. So now what we suggest now, what we do now, we even for so-called two-stage one, but we still assimilate. We don't use this flux as an intermediate product. We still simulate this concentration. It's not a concentration directly to further refine this parameter.
Thank you. Our second speaker is
All right, thank you very much. And I'm very excited to be here. And so I will be talking about one of the strong interests in my group, namely really to look at ozone and vegetation interactions using GeoScan and actually other models. But today, of course, I'm going to talk about GeoScan and the implications for air quality and ecosystems. So we care about this, obviously, because ozone really severely damages crops and vegetation. It affects ecosystem productivity and services. So you can really see, is there okay, great. So you can really see that, under ozone exposure, plants can actually appear like this, having a lot of brown spots, and basically ozone is really bad for vegetation. And at the same time, the arrow can go the other way as well. A lot of us here already know through dry deposition, biogenic VOC emissions, and transpiration, a lot of the things that the plants are actually doing will ultimately affect ozone and actually other atmospheric components as well. So we are really interested in looking at a lot of these kind of like a two-way interactions between ozone and vegetation. So in one of the work that my student, David Yong, who is also here, he has done more recently. For instance, we have tried to use geoscan using RCP emissions from different years for the future to drive geoscan, but using consistent meteorology to really see, okay, how emissions changes can lead to changes in ozone and thus global primary production. So we use, in this study, we use the terrestrial ecosystem model in R, which our group developed on our own, and then we try to see what the ozone impact would be on GPP, gross primary production. So the result is kind of like what some other studies have found as well. So ozone can really have like a substantial impact on GPP, all right? But the range of uncertainty is actually quite large as well. So you can see that depending on your sensitivity of the plants to ozone that you prescribe to the model, the impact on ozone on GPP can be from about 5%, -5% to about -20%. So this is the range is actually large, but the large range is really because of, well, the sensitivity of plants, of photosynthesis to ozone is actually not very well constrained. There are limited experiments that have been done about it, and so this is kind of like really representing the diversity of plants and how their sensitivity to ozone may actually differ. So this is like the current range that we can ascribe to ozone damage on plants. But as atmospheric chemists, we are very interested in to see, okay, so if the ozone is damaging the plants, and plants are doing a lot of things that shape ozone as well, would there be feedback mechanisms that can, like ozone plants feedback that would be out there affecting ozone air quality? So in a recent work done by my former student, Alice Zhou, and she has basically used CLN and geoscan, but only offline coupling them, like asynchronously coupling them. So what she had found is that under ozone exposure, LAI can actually be decreased by quite a bit, all right? And then if you fit the reduction in LAI back to geoscan, then ozone can actually be higher in many places, not by too much, but at least like up to about 3 ppb. And this is really sort of like representative of a strong positive feedback effect that can worsen ozone, okay? Because ozone damage to the plants, then there will be reduced dry deposition, which then further increases ozone. So what we are thinking, okay, it may be cool to actually do something in addition, okay? So this is offline coupling, all right, between CLM and geoscan. I love CLM, but CLM is not always doing, things that are very correctly. So what we're thinking is like, maybe perhaps we can have like online coupling capacity between ozone and plants within geoscan itself. So we think it's kind of cool, okay? Originally, like it's just kind of cool to do so, okay? Well, we are driven by scientific coolness sometimes before we think too much about the scientific value. But it's really cool to do so, okay? So we simultaneously obtain better ozone air quality and ecosystem damage that, just very cool to do. So, but after talking to many colleagues here, and there's a lot of great work coming out of, a group of people here, like in Arlene Speary's group, Colette Hill's group, and Jennifer Murphy's group. A lot of these people have really shown us that, okay, plants are very important in affecting air quality. Plant ecophysiological responses to environmental stress, like climatic stress or environmental stress, like higher CO2, for instance, can reduce stomata conductance, but improve LAI, so on and so forth. Heat and water stress, like drought conditions, can cause the plants to close their stomata. And, all these kind of processes, like, Yu Shen Wang has also worked a lot on that. These kind of issues can really affect the physiology of the plants and ultimately affecting air quality, including ozone itself. So there is a scientific, value to, trying to have plant ecophysiology in geoscan. Especially, well, a lot of us know about Wesley's scheme. The stomatal resistance basically have not really changed its form for more than like 20 years, okay? And we have been kind of stuck with this. Partly because it captured the monthly averages pretty well, all right? I mean, if you're not too picky about it, but we know, from the work, from a lot of people here in the audience, we know that it cannot capture diurnal cycle. It cannot capture the responses to water stress, that especially through vapor pressure deficit or soil moisture, and also it cannot capture day-to-day ozone meteorology covariation either. So I'm not going to answer this question now because of time limit, but this is really a philosophical question almost. Like, why don't we just like put everything into a fully coupled, Earth system model to address these issues? But I'll answer that. I mean, maybe offline or later. So this is what another of my students, Joey Lam, who's also here, has really painstakingly done here. But what he's done is like basically put in juice, okay, using juice mechanism, all of those photosynthesis, thermal conductance, soil water stress, all of these kind of mechanistically really simulating plant processes. And he put all of these things in JuiceCam and then affecting dry deposition and then ultimately affecting ozone. Okay, so this is what he has done. There's also a capability of using photosynthesis to directly estimate isoprene emission, okay? Because isoprene emission is very linked to photosynthesis. But this capacity is not developed yet. We are working on that. So how does the model do? First of all, like what we have emphasized, the new module doesn't break the model, okay? It doesn't cause too crazy behavior. But the red dots are the new with ecophysiology. The blue is the without the normal JuiceCam. So what we have seen is that actually ozone is now higher in general, okay, and then it's actually worsened the overestimation a little bit. This is in summer, so we know that ozone is overestimated in summer, and now the module actually worsened it a little bit. All right, so but we are still working more on the evaluation in progress. So to conclude, ozone ozone can really reduce global GPP. Ozone damage on plants can lead to positive feedback to worsen ozone. But I hope that maybe some of you can be really interested in this new type of development that we have. The ecophysiology model can potentially really improve the representation of ozone dependence on plants and meteorology, especially when we are undergoing global changes like rising CO2, changing climatic conditions, or maybe more frequent climatic extremes in the future. All right. So with that, thank you very much. Yes, yeah.
It's very important to consider the interaction between the industry, but I'm wondering how do you quantify or how do you evaluate the individual process? For example, how do you evaluate the ozone time to dry deposition?
Oh yeah. This is a very good question. So I mean, like we can only do what we have the data for. So we try to really, I like some of my students and some of the other groups here have really tried to get the most comprehensive, dry deposition data sets out there, and we are using an offline model actually to test different mechanisms. And but a lot of us here can tell us, including Anthony, who will present later, no single processes actually outperform the others. Sometimes one is better than the others, but we are doing whatever we can from the dry deposition data that we have to evaluate what kind of processes is better. Yeah, so we are working there, but more observations, the better. Yes, Evan.
So to understand particularly responses for GPP, new measurements such as solar-induced fluorescence are giving us a really new window into photosynthetic activity. So could you just comment on the model development line of where you're bringing in or where you plan to bring in perhaps SIF measurements to help evaluate the model?
Well, thank you very much for that question. I think like as a like atmospheric chemist myself, like even getting to do the biogeoscience stuff is like sometimes it's a big window out there for me to explore. So I don't know, like it seems like by talking to people like you, we use whatever the best kind of GPP product there is to evaluate our model. And but then what we have found is that even if you have very good GPP like observation per se, but then the experimental deficit of the ozone plant response to ozone is still one of the major uncertainty. Yeah, so the uncertainty is like if you have sorry, it's okay. So yeah, I mean like with the range itself can actually be even larger than the uncertainty in GPP estimates. Yeah, so I myself would feel like we should do more experiment on how atmospheric pollutants would affect plants on a greater variety of issues, and also perhaps bringing in machine learning on global data sets to estimate the effect as well. But in terms of GPP per se, I would like to see what you think as well. Okay. Yeah.
I
I have
Yes.
one question.
Yes.
You show positive feedback.
Yes.
When you look at the impact of ozone on plants, but you didn't calculate the effect of biogenic emissions
Okay.
caused by the damage of plant. Do you think you still have positive feedback?
Oh, actually, the study does consider the impact on biogenic emissions. Yeah, it does have. So the interesting thing is that for a lot of places, especially in the tropical regions, dry deposition is actually the dominant driver because it's low NOx. So actually, when biogenic emissions is affected, the positive feedback is even worse because if you have ozone damage, you have less isoprene emission, then you would actually have even more ozone because isoprene can actually chop off the ozone in those low NOx region. And what we have found is that in mid-latitude, for instance, the two effects, lower dry deposition and lower isoprene emission, kind of counteract with each other. Yeah, but the overall effect is still a positive feedback. But in some places, like in China, somehow it is actually a negative feedback because of isoprene. Yeah, so
Okay.
so we do consider that.
Okay, thank you. We have to move on.
Okay.
The uncertainty are largely determined by the natural aerosol processes, for example, the fire, especially in the pre-industrial period. That is because for any climate forcing assessment, the baseline is the pre-industrial. And the cloud forcing effect is actually very sensitive when the condition is very clean. We know that in the present day, the fires are usually monitored by the satellite. But before the satellite era, we don't really have a lot of information on fire. And here we're trying to use the Antarctica ice core records of black carbon deposition to get the history of the fire in the southern hemisphere. And in total, we got 14 different ice cores. And you can see they cover a wide range of geological locations over the Antarctica. And the different ice cores can be sensitive to different the emissions from different continents. So we think that this data set can be very valuable for evaluating our the interpretation of the ice core data is still quite challenging. So that's where the model can be very useful. We're using the GeoScan model coupled with Thomas. That's an aerosol microphysics module. We first did the simulation using the CMF6 emission inventories for the present day. So basically, the biomass burning is the same as GFAT4 for the present day. And here I show is the black carbon deposition flux over the Antarctica. And there's a comparison between the measurement and also the model. And we can see that the model is doing a pretty good job. This is actually surprisingly good because the deposition flux can change several orders of magnitude from the source region to the Antarctica. And we can still capture this spatial contrast. However, there's a problem for the pre-industrial simulation using the CMF6 emission inventories. We can see it can still capture the spatial contrast, so the correlation coefficient is quite high, but the magnitude is biased low. And this bias is more obvious, from this, the plot for the trend. So here I just normalized everything to the present day value. That's how we get the trend. And we can see from the ice core measurements, the black carbon deposition flux did not vary too much from the pre-industrial to the present day. However, based on the CMF6 inventory and the GeoScan simulation, we can see there's a sharp increase. And if we further break down this increase, we can see there's a contribution from the increasing anthropogenic emissions and also the biomass burning emissions increasing. So we think that the anthropogenic emissions are increasing. This is reasonable. So we know that we emit more particles now. But for the increasing trend of the biomass burning, so there's a very large uncertainty. So if we take a closer look at the emission inventory we're using for the biomass burning, so the emission inventory actually largely rely on a fire comparison project. So it's called FireMap. And there are 6 different fire models. And we can see they don't agree with each other. So some models predict that the fire activity decreases over time, but some other models predict there's an increasing trend. So the key uncertainty here is we don't quite understand how human activity affects wildfire. The traditional understanding is that the fire activity increases with population density because most of the fire are caused by human. But the new understanding is like human can actually suppress fire. And the one mechanism we think important is called landscape fragmentation. So actually human can change the land use and makes the landscape more fragmented. That can make the fire spread slower. Based on this new understanding, we did fire modeling using a model called LPJ LM-Fire. So there are 2 parts of this model. So the LPJ part is a dynamic vegetation model, and the LM-Fire is a fire module. Basically, we also scaled our output from the model by the present day burned area observed by the satellite. This is to correct the systematic bias in the model. We can see that there's a difference between the CMIP6 emission inventory and the LPJ. The upper panel shows the change in black carbon emission inventory from the pre-industrial to the present day. And we can see that in the CMIP, in the southern hemisphere, so the biomass burning emission is increasing everywhere. If we look at the number, so the total emission of black carbon changes from 0.6 teragram to about 1 teragram per year in the present day. However, in the LPJ, we see there's a decreasing trend in the southern hemisphere. And in the northern hemisphere, so they are basically similar. When we implement the LPJ LM-Fire emission inventory into the geoscam, we can see that we can pretty well capture the trend observed in the ice core. Basically, if we compare the 2 emission inventories in the southern hemisphere, the LPJ is about twice as the CMIP, but also the locations of the fire moving closer to the Antarctica. And then we're also interested in the cloud in the aerosol forcing. So basically, we're changing the baseline of the aerosol forcing assessment. And the cloud albedo forcing is very sensitive to the pre-industrial aerosol. And if we look at the number, so the average cloud albedo forcing using the CMIP6 biomass burning inventory, so in the southern hemisphere is about 0.56 watt per square meter. And if we use the LPJ, so the value is attenuated by about 40%. And here I just leave my summary here and happy to take some questions. You mean the can yeah, so we actually okay. So your question is about the let me show you something. So we actually have one additional like a glacier record. This is from the Andes, and so we hope that we can see some signal from the Amazon and from the Amazon forest. And we can see that still the LPJ model performed better than the CMIP6.
What do you assume for biofuel use? Could there be any meaningful trend there?
Yeah, so we actually use the CEDS emission inventory, and the biofuel is included in that inventory. But we classify that as anthropogenic emissions. So yeah, there's definitely a trend in that.
Could the changes or the trend in the black carbon and ice core caused by the other factors like the transportation change or circulation change? Because the fire source is quite far away from Antarctica.
Yeah, definitely. So, but now we're using, this is an offline coupled model, so we don't have the feedback to the climate yet. But we can basically use the same emission inventory and using the fully coupled climate model to look at those effects.
One more question from Jim.
How injection height?
So currently we are just injecting everything to the ground level. That's the limitation of the Thomas module. But we actually compared with the different injection height. It does influence the concentration, the surface concentration near the sources. But actually the deposition in the Antarctica did not change very much.
All right,
Okay.
thank you.
Do you know where USBs go on a PC?
Which one?
Where a USB? Where does the USB show up on a PC? I don't know how to use a PC. Oh, maybe it's here. All right, right here. This is yours, right?
You just want to change it, right? So duplicate. Okay, thank you. Hello everyone, I'm Xu, and I'm now at Newest. And the title of my presentation is Fire Air Pollution Reduce Global Terrestrial Productivity. And this work is done by me and Professor Nick Younger at University of Exeter. So why we care about fire? Fire is an important contribution to global carbon budget. From the global fire emission database, we can see a large fire emission in tropical regions. Globally, fire emits about 2 kilograms carbon per year. The land carbon simulation shows that global land uptake is weakened by fire emissions. In addition to carbon emission, fire also generates air pollution. This includes aerosols and also the formation of ozone. We know that this plume will be detrimental to public health in some downwind regions. More than that, fire plume also has some impact on plant health. The aerosols will affect radiation and also change temperature precipitation. This will affect plant photosynthesis, while the ozone will damage plant through the stomatal uptake. So in this talk, we are going to quantify how ozone and aerosols from fire influence ecosystem productivity. First, let's see how ozone affects photosynthesis. The ozone is uptaken by plant through the stoma, which is a small pore on the leaf surface that regulates the exchange rate of CO2 and water vapor between leaves and the atmosphere. Generally, the higher the ozone concentration, and it will cause higher damage to both photosynthesis and stomatal conductance. In the model, we use siege adult skin to quantify such damage on the global scale. Here, we do some evaluation of this skin. We plot the GPP sensitivity to ozone for 6 main species, including the evergreen broadleaf trees, temperate evergreen trees, temperate decidual trees, C3, C4 herb, and also crop. The blue point is the model simulation, and each red point is observation from literature. And the y-axis is ozone, is the GPP change from 0 to minus 80%, and the x-axis is the ozone concentration. Generally, with the increase of the ozone concentration, all species show that GPP decrease gradually, and they have different sensitivity. We can see that the model generally capture this response for different types of the vegetation. For aerosols, in this talk, we are going to talk about only the aerosol impact on radiation because change in the temperature and precipitation is more complicated. The aerosol will decrease direct light but increase diffuse light. This increase of the diffuse light is benefit for plant photosynthesis. But the reduction of the direct light is not good for plant health. Here we found 24 sites on the global scale that provide long-term observation of carbon flux as well as the diffuse radiation. Then we separated the moment that is dominated by diffuse light or dominated by direct light. Here we can see each plot represent a result in one site. And the blue and the green here is the response of the GPP to diffuse light. And the red and the yellow is the response of GPP to direct light. We can see for the same amount of the radiation for most of the sites, GPP is higher when the light is more diffuse. And the blue is the observation, the green is the model. Then we calculated the slope of these two lines and showing here. We found that the model generally captures this GPP response to diffuse radiation. So after this evaluation, we come to see our method. In this study, we use 3 different models. First, we use JustCam model to simulate fire perturbations in ozone and aerosols. The fire-induced ozone will be used as the input for this vegetation model to simulate GPP change. Then the aerosol from the fire will be used as the input for the radiation model to simulate a change in radiation. This will be used input for vegetation model to simulate GPP change. First, let's see the ozone effect. Without fire, we can see ozone generally located in northern hemisphere, while for the fire-induced ozone alone, it will increase ozone by 5% globally with the regional maximum in Central Africa. And the non-fire ozone will cause damage to GPP, especially in Eastern US, Eastern China, India, and also Europe. On a global scale, it will damage GPP by 3%. For the fire alone ozone, it will cause damage, especially in Central Africa. And that will cause a GPP reduction by 0.7% on the global scale. For aerosols, in our simulation, we show that aerosol generally increase GPP. In this plot, blue means decrease and red means increase. But most of the increase located in arid regions, especially in North Africa, also Western Asia. On the global scale, fire-free aerosol increased GPP by 0.7%, and fire aerosol caused very limited impact. However, if we remove cloud effect, we found that aerosol has a very large impact on photosynthesis. That for clear sky condition, fire-free aerosol will increase GPP by 0.8% with regional maximum of 20% in China. And fire aerosol will increase GPP by 0.7% on the global scale. However, because of the dense cloud, especially in some forest regions, it will mask the aerosol effect. Finally, we put aerosol effect and the ozone effect together. We found that without fire perturbation, the effect by ozone and the aerosols shows the contrasting spatial distribution with ozone damage located in wet regions, but aerosol effect fertilization in arid regions. However, for the fire, we found that ozone and aerosol effect, they overlap and ozone effect dominant. So on the global scale, the fire pollution caused a net reduction of 0.6% in GPP. So in this study, we reveal a missing mechanism that fire emission will cause additional damage to global carbon cycle. Okay, with that, I'd like to thank you and take questions.
Why do you see such a large relative change in the Sahara Desert, which is barren? Is it just that it's a small change on a small GPP?
The main problem is that the cloud cover in that region is very limited, so that the aerosol effect can be shown there. in many forest region, you know that precipitation is abundant and the cloud cover is dense. This cloud cover will cover the aerosol effect.
If there's any significant effect from the deposition of the aerosols and surface on
In our study, we didn't consider this effect, but I think that it's important, especially for some nitrogen effect. Maybe in the future, we can consider that.
It's a very related question. So I understand this is about fire-air pollution per se, right? But then at the same time, the fire can actually really return a lot of nutrients to the ecosystem, and ultimately may actually be, good for the ecosystem. I'm just wondering, have you kind of compared the relative effect between the fire per se versus fire-air pollution effect?
We haven't right now, because the model does not have the nitrogen cycle. But in the future, we are going to implement such module into the model. Okay, thank you.
Next speaker is Xiaolu from PKU.
Hi everyone, I'm Xiaolu from Peking University. Today I would like to introduce a new climate chemistry model, BCC GeoSchem. So basically BCC is a Chinese climate system model. And what we do is to couple GeoSchem into the model as a chemical module. I would like to start with a figure in IPCC AR5. So this figure is showing you all 39 models included in SIMI5 project as well as a component. We can see that there are only 10 of the SIMI5 models include interactive atmospheric chemistry in the model. For the rest, including all the 5 Chinese models, chemistry is just prescribed in the model. So this situation has motivated the Chinese Research Institute start to consider chemistry in their climate system models, including the BCC CSM from the Beijing Climate Center. BCC CSM is a SIMI project member from SIMI3, and it has been remarkably improved from its initial version with regard to the complexity and resolution. Now, BCC CSM is a fully coupled climate system model in which the atmosphere, land, ocean, and sea ice will interact with each other through the cupola. The present version of BCC CSM also includes an earlier version of Mozart for chemistry, and the model can actually well simulate the historical climate change. Now, BCC is hoping to update its chemical model to GeoSchem, which we are happy to see. But one important first step is to re-engineer the classic GeoSchem into a grid-independent model that can be performed across multiple nodes MPI. And this has been achieved with the recent development of GCHP, which has been introduced in Daniel and Randall's talk earlier in this meeting. So I would like to skip this. With all this previous effort, I would like to introduce a framework of BCC GeoSchem. We start from the atmospheric model, which is the 3rd generation of BCC IGC9. So it is a global spectral climate model. And this model will use a relatively coarse resolution of about 2.8 degrees horizontally and with 26 vertical layers. The land model is BCC AVRM, so it is a comprehensive land model that will simulate the land surface and plant activity process. And land and atmosphere will communicate with each other in the model. To simplify the model, we prescribe ocean, sea ice, and external forcings in the model as boundary conditions. The chemistry is using GeoSchem version 11.02, and it includes detailed gas aerosol chemistry, as many of you are very familiar with. The stratosphere chemistry is using Linos. The dry and wet depositions are the same as a classic GeoSchem, but one improvement is that we have reconciled the plant functional types in the GeoSchem dry deposition with that used in BCC land model. So this is done by eliminating the dependency of the ozone map in the classic GeoSchem. For emissions, we do not use HEMCO at this stage, but we directly process anthropogenic and biomass burning emissions from SIMI6 in the model. We have also included a number of natural emissions. For example, the biogenic VOCs are calculated based on methane in the land module and then passed to GeoSchem. So all of these components together build the 1st generation of BCC GeoSchem. In the next few minutes, I would like to show you some evaluation of the model. We have used the model to conduct a 3-year simulation driven by SIMI6 emissions. Here we compare ozone with OMI satellite observations at the middle troposphere where OMI has a high sensitivity. And we can see the model well captures the higher ozone in the northern mid-latitudes with pretty high spatial correlations for all seasons. The model tends to underestimate ozone over the northern mean latitudes and overestimate at the tropics, but the global mean bias are within 1 ppb. We compare model ozone to global ozone zone observations categorized by 9 regions from south to north. The model will reproduce the vertical profile of ozone, especially in the lower and middle troposphere. But the model tends to underestimate ozone at the upper troposphere and in the stratosphere. We further compare the seasonal evolution of ozone at different vertical layers. And we can see from the figure that model shows pretty good simulations in capturing the seasonal variation of ozone. The bias are within like 8 ppb globally, but except at the polar upper troposphere where the model shows high low bias. To understand the bias, we'll also diagnose the budget of ozone and OH in the model. We find that the global burden of tropospheric ozone and OH are in good consistent with the literatures, but again, the model shows low proportion of ozone at the upper troposphere compared to other studies. The chemical production and loss of ozone are somewhat higher than classic GeoScan, probably due to difference in meteorology and emission, but still falls in the range reported by other models. The largest difference appears to be STE, which the model shows notable low bias compared to other models. So we are still working on to figure out a better way to identify STE in the model. We have also evaluated other gas and aerosols and compared them with satellite or surface observations. So here I'm not going to the details, but would just like to share that the model can generally capture the spatial patterns and also the magnitude of these traces, but we will have some seasonal or regional bias. And finally, we have used the model to conduct a long-term historical simulation for about 40 years. So this movie is showing you the evolution of monthly mean ozone at 500 millibar. I'm not going to make any scientific points here, but I just want to share with you that the model can be reliable and stable for such a long-term historical run. So it should be ready for some relevant studies on like long-term trend analysis or interannual variability analysis. To summarize, we have built and evaluated the first generation of BCC GeoScan. The model shows pretty good performance in atmospheric chemistry, especially for ozone. We will try to evaluate radiative feedback in the next step, which can be more complicated, and we'll try to implement HEMCO and UCS in the next generation of BCC GeoScan. And at last, I would like to thank a lot of contributors to this project. We've spent like a few years to reach this step. With that, I would like to stop here and take questions. Thank you.
It looked like in the online version you have much more washouts of HNO3 constitution.
I'm sorry?
It looked like the washout in the table where you compared the online versus the offline, that the washout rates look much higher in the online one. Do you think that's because of the online convection, that it's much stronger than the offline?
It means a normal ozone, or I cannot catch the question.
The washout rate, I think it was HNO3 that you showed.
Okay. The wet position of HNO3. Okay. I haven't actually. I have noticed that, but it may due to some problems in wet scavenging. So we now treat the convective transport and wet scavenging both in GeoScan, but this will lead to some, inconsistency compared to BCC, the wet depth. So that might be the problem. And also NO2 emissions in synthesis inventory is actually much higher than previous inventory.
We have been seeing similar issues
really?
in the online shield, so we can.
Okay, cool. Yeah.
Do you think the resolution of the model could contribute to the difference in the STE?
I'm actually not sure. Yesterday we have a poster by, I think, from Kunali from they compare the difference using different resolution, but I think the difference is no more than like 50 paragrams. So this low bias, I think, shouldn't be contribute to the resolution. It should still be some problems in the stratosphere chemistry or in the dynamics. Yeah. Is that?
Do you have? You've implemented a version of GeoScan to BCC.
Mm-hmm.
Do you have plans on how to stay up to date or to roll in new developments in GeoScan as it advances? So
you mean once GeoScan is updated, how to couple GeoScan? So actually, this will be not very hard. You still can put the new GeoScan into BCC, but we almost need to add some lines, for the diagonals or other things. Yeah.
So I have a question. How long did you take to run the model for 150 years?
Actually, so one natural day can run one model year. So it's like 1 month for like 30 years, based on 64 codes. Yeah.
Okay, thank you, Sean.
Hello, everyone. I'm Forrest Lacey, an ASP postdoc at NCAR, and I'm going to talk with you about some of the work that we're doing linking CSM to GeosChem. So the motivation for this and why we want to link the models is that really GeosChem as a community has the desire, as has been shown in the previous talk, to link to an Earth system model. And preferably this is an open source model, which CSM is. This specific model framework would allow GeosChem users to study upper atmosphere impacts, and also the ability to run future scenarios without offline processing of meteorological files. This is something that we would be able to get from the NCAR Lens project or CMIP6 experiments. As part of the CSM community, we really hope that we would decrease our grid complexity using a tool like HEMCO or some of the emissions processing capability that you have. And additionally, we would get a lot of community support for some of the testing and validation of new chemical mechanisms. That's something that's really been highlighted by the GeosChem community that would be of a lot of value to CSM. In addition, we would spread the user base of CSM. And just another bit of motivation from the NCAR side was this video that was sent to us in May from Lu Hu's paper. And this is the NASA GEOS-5 12.5 kilometer nature run with GeosChem chemistry. We thought this was a very neat visualization, and we wanted to do something similar. So the Community Earth System Model, or CSM, is basically a model framework that combines a number of different elements of the Earth system into a specific model. And as we've shown here, we have the land model, or CLM, sea ice, atmosphere, land ice, ocean, and these all get passed through a coupler that enables the bidirectional feedbacks between each of these individual models. For most of the rest of this talk, I'm going to be talking about CamChem, which is specifically a more complex version of the atmosphere model where we have full chemistry. And as you've seen some of these slides before over the last 2 days, this is the framework that we're thinking about for the initial implementation of GeosChem within CSM. So right now, if we break out the atmosphere, we have dynamics that are controlled. This is our FV dicore. And then we have physics, which currently are specified by the Mozart chemical mechanism. And we envision being able to drop in GeosChem instead of the Mozart mechanism. And then as a side bullet, we also have HEMCO coming in and determining some of the emissions, initially as a pre-processed variable. In the future model frameworks, what we'd like to do is have the opportunity to choose which parts of GeosChem specifically you want and which parts of Mozart or any of our existing chemical mechanisms you want. So you could choose GeosChem aerosols and tie them back into the dynamics and radiative transfer code within CSM or anything like that. We could pull halogens out of GeosChem, put them into our model, and this is all being defined by the System for Integrated Modeling of the Atmosphere, or SEMA. And this is our next generation of NCAR models. Now, where it gets a little bit complicated is with model resolutions. So here is the basic framework for model resolutions within GeosChem, where you have the global 4x5 and 2x2.5. In addition, you have a number of nested grid simulations. And then third, you have GCHP, which operates on a cube sphere grid. If we're looking at CSM, grids become much more complex, which I've tried to visualize here. Basically, you can query the number of grids that you have available, and you get an output list like this. Which we'll keep going. And basically what this is this is 255 different supported grids that are variations in either one of those modules. So in the ocean, in the land ice, sea ice, or atmosphere, land, sea ice, and choice of dynamical core. Now, knowing this, what we envision with GeoSChem being part of the CSM framework is that we would define a specific comp set, and that's how we refer to these combination of grids, that would be the GeoSChem package within some specified grid resolution based on your science question. And kind of to envision what this would look like, these are two comparable grids, one of them in CSM. So here, this is our cubed sphere spectral element dicore grid that we use for looking at CONUS. And then this is a visualization of a stretched cube sphere grid with 0.25 scaling. The one on the right goes down by a factor of 0.125 scaling, so it's a little bit higher resolution. But as you can see, this is a very similar framework that would be able to do between GCHP and CSM2. In terms of chemical mechanisms, the current mechanisms are actually fairly comparable. The Mozart TS1 mechanism has around 220 species and 548 reactions, whereas the standard GeoSChem chemical mechanism has around 241 with 725 reactions. In addition, we both have more advanced chemical mechanisms. So the TS2, which is in preparation right now, increases the species by about 100 and increases the reactions by about a factor of 2. And this is similar to the VBS-based SOA scheme done by Almahodzi and Dusong Zhou, who is also implementing this into CSM. And one of the questions I get a lot is, how much is this going to cost for a fully coupled Earth system model approach? And here you can see, this is based off the benchmark timing runs. We're at pretty similar computational costs. And one thing that we do have is a new advection scheme in CSM that reduces the impact of adding additional advected species. So anything over 100 species, transport of them is free based on the CSLAM mechanism. And the baseline CAM-CHEM, which is CSM with full chemistry, does require high performance computing capabilities. And then I want to jump to this. This is the grid layout that I showed previously. And this is now a fully coupled Earth system model running at 12 kilometers. And that's very comparable to the GEOS5 Nature Run. And this is completely on an open source model. So for the current development and next steps, Harvard and MIT have been awarded funding from NSF to look at combining the CSM GeoSChem. And we're looking at HEMCO as an offline emissions tool. And we're trying to validate this using a number of data sets so we could use your data. And phase 1 will probably start in September of this year. And I will take any questions.
Can you please comment on NCAR's plan for CAM-CHEM?
NCAR's plan for CAM-CHEM, basically, we are retaining CAM-CHEM as a model. It's going into what we're calling the next generation of NCAR models called Musica, which is the multi-scale infrastructure for chemistry and aerosols. But that is basically what CAM-CHEM and WACM are now. It'll be a combined model that you basically get to choose your layout based on your science question of need. Do you want to study upper atmosphere, or do you want to do regional air quality modeling?
This is really exciting work. I want to know, could you just talk a little bit about, if we're interested, say, with GCHP, want to use the couplers into some of the other components of the Earth system model. How far, once you guys get farther along, how much extra step do you think would be for us to begin to look at coupling into those other components?
So the way that we're trying to do this, and this is, again, goes back to the next generation of NCAR models, is through this system for integrated modeling approach, it's SEMA. So what we're doing is we're trying to say that this will use any CPF compliant model and go in and take whatever modules we want. So we can pick and choose different modules. So if we want specific parts of GeoSChem, those can then be passed in through the coupler completely independently. So it should handle that in our next generation of models. Right now, we don't currently have that capability, but that is our long-term goal, is to be able to choose different components based on your science question and what you're interested in, if that answers your question.
I just wasn't clear if you're talking about GeoSChem as a column model or as the full, like GCHP is a full offline model for which, for example, atmospheric tracers could be absorbed into the oceans and re-emitted in a self-consistent fashion. If you had a coupling system that doesn't require the dynamics or the thermodynamics to be explicitly coupled.
Yes, so those are still some questions that we have to answer in how much of GeoSChem do we retain versus how much of CSM do we retain. And so we don't really have an answer for that yet, but that's something that we're going to be explicitly looking at as we start this process.
Okay, one more quick.
Is that the chemical mechanisms between Mozart and GeoSChem similar? Do you have any sense of what the effect of swapping these out would be on ozone and PM?
We don't currently, and that's kind of why I am asking the GeoSChem community for your model data. So for the specific cases that I looked at, so for US 2013, we have a lot of runs in CSM, and we can, using current data, we would be able to estimate the bias between GeoSChem and CSM. And I think that's part of the first step moving forward with this model approach. But currently, we don't have a good idea of what that quantification is. Thank you.
Okay, good afternoon, everyone. I'm Anthony Wong. I'm a graduate student of Professor Jeff Gaddis in BU, and all of my collaborators is around this conference. Great. Many of them, this is my first time to talk with them face to face. So today I'm going to talk about my work on dry deposition, a gaseous dry deposition. So in chemical transport models, gaseous dry deposition is always parameterized as a level of resistance. Basically, it incurs the effect of like vertical mixing, stomato sink, and non-stomato sink. But in current theory, basically stomato resistant, we have ecophysiological theories that said that like it is a function of like plant functional type, radiation tip transfer, water temperature, and carbon dioxide. And for non-stomato model part, actually field measurements suggest that it's very messy and it is very species dependent. Thanks to Amy's presentation, now we know that like in GeoSChem, actually we miss out something like the effect of CO2 and water vapor for the stomato resistant, and for the non-stomato resistance, it's practically some sort of like land type specific constant with some scaling to leaf area indices. So we explore the impact of the choice of surface sink parameterization that are applicable in global model to explore how they affect simulated surface ozone concentration. These four configurations are not exhaustive, but are representative of current available approaches of modeling surface resistance. The first, DAP98 is the GeoSChem parameterization. The second parameterization is replacing the stomato resistance of the GeoSChem ones by the photosynthesis stomato conductance model. The third one is the Zhang et al. Scheme, where like stomato resistance includes the effect of water vapor, and the non-stomato resistance includes the effect of canopy wetness and canopy to soil turbulent transfer. And the fourth one is the Zhang, that is replacing the stomato resistance of the Zhang scheme by the Borberry model. And we run these four deposition parameterizations offline for 30 years with MERA2 and combine it with 1 year of GeoSChem sensitivity simulation to explore the impact of choice of dry deposition parameterization on model surface ozone. So we found that it does affect model surface ozone, but in what way? Okay, so basically, there are a lot of nuances, but I want you to focus on hydroclimate, where like in July, we find that in tropics and Mediterranean, where like there are a lot of area there is in dry season, the GeoSChem parameterization simulate a high deposition velocity than all other schemes. And in India and China, where the soil is wet enough to sustain photosynthesis, actually the photosynthetic scheme simulate higher ozone dry deposition and therefore less surface ozone. And in December, especially over Indochina, where the dry season is pretty strong, the geochem parameterization does not seem to capture the observed big drop in ozone dry deposition. And all these effects leads to up to 8 ppb of monthly mean surface ozone uncertainty. And for actually, because we have 30 years of simulation data, we also look at the intervening variability, where actually in July, the intervening variability of dry deposition can lead to intervening variability of surface ozone up to 3 ppb. And we found that the geochem scheme is especially sensitive to leaf area indices, while the other scheme are more sensitive to climate. So, but if it is important, then we have to constrain it, but what can we do? So we first have to look at what observations do we have. First, we have direct trace gas flux observation, like what Manga did in Harvard Forest. So it is species specific and it tells us about the total deposition. But at the meantime, it is spatiotemporally very sparse, as you can see from the graph. And there is no standard archive for relevant micrometeorological and soil data, which is like the input of the dry deposition models. Whereas we also have recently, thanks to Jason Ducker and like Christopher Holmes, and basically we can derive the stomato resistance using Kalman-Monteith equation from the global network of water vapor flux measurement called FluxNet. I'm sure many of you are completely familiar with it. So it has complete micrometeorological data and radiation data coming with from FluxNet, which is the input of the dry deposition modules. And it has excellent global coverage comparing to direct trace gas flux measurement. And also stomato resistance is not species specific, so that constraining stomato resistance can help us to constrain also not only ozone uptake and ozone damage, but also gives us information about NO2, SO2, and ammonium deposition. But it does not directly fit to total deposition velocity. So collocated measurement can help us to gauge if a better stomato resistance leads to better deposition velocity. So, but that's it. The answer is it is complicated, but at least in Harvard Forest and Hutiala, where the stomato uptake generally dominates during growing season, actually it works and it improves the prediction both in hourly and daily time scale, and both correct the bias and error of the Wesley scheme. But this is directly applying the SymFlux data to replace the stomato conductance, but the SymFlux is not available everywhere at any time. So we have to explore how SymFlux can help us model stomato conductance. So this time, with a messy data set, what can you do? Machine learning. It works pretty well. And by applying the machine learning stomato conductance back to the Wesley, by replacing the stomato resistance from the machine learning scheme to the Wesley scheme, actually we can see similar magnitude of improvement of the dry deposition in both daily and hourly time scale. And it works for both Harvard Forest and Hutiala. But can we do that in global scale? This is possible, but with some other extra remote sensing and climate indices, and across different biomes, the performance is pretty good. Like the error is at the order of 30%, and the R square is like 0.5 to 0.75, which is pretty good in terms of global data. And implemented back to GeoScam potentially improves both gaseous dry deposition and stomato ozone uptake simulation, which is both very important processes. But the speed and software engineering overhead can be quite a concern, as what Sam has stated from his recent paper of deep learning of dry deposition. So I'll leave my conclusion here and take questions.
There have been measurements of enhanced ozone dry deposition to wet surfaces, and certainly surface ozone is often lowest when it rains. And I wonder, do you know what mechanism could be involved?
Yeah, basically, there are a lot of lab measurement rather than field measurement that basically there is some leaching of antioxidant from the plant leaf to the water film, so that like basically it reduces ozone directly much more effectively than the cuticle wax. But Olivier Clifton argued that like actually wet soil is not good for ozone uptake. So it's like that's why I said that the non-stable buttermilk is pretty messy and like, yeah. Okay.
Thank you. Final all of the
I think it's Windows.
Oh yeah. Hello, I wanted to introduce our recent work on how the changes of wet scavenge impact the simulation of nitric ammonia in geochem. Nitric and ammonia are very important aerosols. They take account for large parts of PM 2.5 were polluted regions, and they are very important species for aerosol macrophysics because the mass concentration of nitric ammonia also regulate the concentration of ammonia, which is important for new particle formation. And the concentration of nitrogen and ammonia also contributed to particle growth, which impact the number concentration of CCN, and they impact aerosol indirect radiative forcing. And it is well known that published by some many previous publications that in geochem, usually nitric ammonia are often overestimated. And the possible reasons suggested by previous studies include the uncertainty of N2O5 chemistry, emission of NOx, and uncertainty of OH and NO2 oxygen by OH, and the dry deposition of nitric acid gas. And in this study, we have another view for this problem. We found that maybe some changes of wet scavenge can reduce this bias in geochem. One thing is about the rain out. When we look into the rain out, we found that in traditional geochem, we assume a constant volume for in-cloud condensation water. But after GEOS 4 in GEOS 5 and MERI 2, we can use the cloud information and the rain information to represent in-cloud condensation water in the model. So this the equation 2 is the method we use to represent in-cloud condensation water in our new method. And put this into equation 1, we get the simplified equation 3. I think the physical meaning of this equation is very straightforward. It means that rainout is the part of cloud water converted to rainwater. And this slide shows the global distributions of in-cloud condensation water and the friction of rainwater in cloud condensation water we got from the MERI 2 meteorology. Because for MERI 2 meteorology, they are usually for 3 hours averaged. So for the equation 2, the delta T equals 3 hours here. If you look into this global distribution of in-cloud condensation water, you will find that they are usually varied from 0.1 to 5 gram per square cubic meter, and it has a significant change of at a different location. The values are quite different, and if you look into different seasons, you will find that these values are also changed with the time. And look into the right picture, you will find that about 60% of in-cloud water will finally be converted to rainwater in MERI 2. And it has some significant uniform distribution. At the tropical regions, and the continental regions, and the mountains, you will find that the friction of rainwater is pretty high. And over some marine region, especially for the cloud rooms, you will find that the rain friction is very low. So it's agree with the physical that over some cloud rooms, the lifetime of cloud is very long, and most of the cloud water just evaporate, go back into the atmosphere. But for tropical region and some continental region, if there are a lot of cloud, finally they will become the precipitation. Okay, another change is about washout. Washout is in traditional, we use the equation 1, equation 2 to calculate. And in older geochem, we use the lambda for equals 1 and the B equals 1 to represent aerosol and nitric acid. And in the I think maybe after geochem version 10, Chao has introduced, we use another values to for fine model aerosol, and we use another And in this study, we suggest the value for lambda equals 2 and the B equals 0.6 to represent the nitric acid wash. And this shows the picture from the Wang's work. It shows that the different washout rate from the observation and from theoretical calculation. And the marks are from the observation, and the lines are from the theoretical observation. A general idea is that we found that the theoretical calculated values are often much lower than the empirical values. So with this idea, we use the empirical values, and we calculate the difference of the washout rate for nitric acid is about 10 times higher than the one in JOS 12. And it's not moving. Okay, it's here. Okay, this is the validation of nitric acid, nitrate, and ammonia over United States. We found that after applying the changes of washout, the bias of this species has been significantly reduced over United States, and this result has been published in the GMDD. If you want to have some detail, look into some detail, you can just go to this paper. And we'll scale to the comparison over Europe. And this is the changes of nitric acid over Europe. We found that after applying the new scheme, the bias of nitric acid has been significantly reduced over this region. And this is for nitrate. Nitrate usually is overestimated in winter time. After applying the new scheme, it has been reduced and go to very close to the observations. And this is for ammonia. Ammonia has been a problem. Usually in the old version, it's 2 times higher. But after use the updated scheme, the values are very close to the observations. And we also compared the values of China. It has some improvement, but still has still has a lot of disagreement. And we also look into the impact on sulfate, and we found that directly use the updated scheme, we will cause the underestimate of sulfate over United States and over Europe. But we applied some upgrade of the cloud pH calculation and the rainout efficiency of aquachemistry mass, and this bias has been successfully reduced. And we also look into the impact on BC and OC, the same problem. Directly use the new bioschemistry scheme will cause the underestimation, but if we modify the rainout efficiency, this bias can be reduced. And this is my summary. And I just want to focus one thing is about the rainout efficiency. This is why I mentioned a lot of times it can be used to recover the underestimation for the sulfate and BCOC. Rainout efficiency is a very important parameter, but it's hard to parameterize with the bulk scheme, because the rainout efficiency, the physical of rainout efficiency is that under certain meteorological condition and humidity condition, how much aerosol can be active into cloud droplet. Then it can be do with the rainout process. For nitrate and ammonia, it's no problem because it's most of them are on larger particles. So most of them are easily go to cloud droplet and fully be removed by the rain out. But for BC and OC, even they are agent and they are hydrophilic, but due to their couple coefficient is very low, and so yeah, so they cannot be fully cleaned by rain out. Oh, that's all. I exactly compared with the surface with ATOM, and the agreement. I saw some improvement at the south part of Alaska, because for ATOM period, it has one truck is from the California to Alaska. For that side, I see significant improvement. But for other region, I think there are some places are better, some places are worse for surface. But for BC, I did not have a look.
Thanks. I wondered, have you or anyone else looked at our sulfate bias as you change the model time step for wet scavenging? Because the way we do it makes you sensitive to the operator split. And so I believe your bias would depend on how big or small your wet scavenging is.
Oh, that could be, because I think Pantis has published a paper in 2018. This is that the time step also has a very significant impact on the wet scavenging process due to their study with Wolfcam. But based on my study, I think the impact, because I also do some study, I think the difference is about 10% or maybe, yes, 10%. The difference is about that.
Okay, thank you, Ben. Yeah, it's time for poster presentations. So,
Sugar? That's okay. Okay. I'm not Alfred, it's my student, but unfortunately he couldn't be here. So I'm going to be standing at his poster on his behalf. Charcoal production and use is increasing at a rate of 7% per year in Africa. And so it seemed vital to try and understand what the impact might be on air quality and climate. And so what Alfred has done is he's developed an emission inventory of the charcoal supply chain in Africa and is embedding it in GeoSchem to try and answer these specific questions. So if you want to find out more, please stop by his poster.
Hi all, I'm Alex Carambelis. I'm a postdoc at Columbia University. And for this project, I'm at B24. But for this project, we were interested in using TOMAS to understand differences in the aerosol microphysics on average and then seasonally. So here we're just showing the excess PM2.5 and excess CCN during the biomass burning season. So just trying to get a sense of what that means for total aerosol composition, how those changes during the season, and what that means for climate impacts. So if you can come by my poster if you know anything about TOMAS, that would be wonderful. Thank you.
Hi, I'm Sam Silva. My poster is at B25. I added a vegetation canopy model to GeoSchem without slowing it down like at all. And it messes with a lot of stuff, including dry dep and Megan 3. And if you want to chat about any of these things in red or anything else, come on by.
Hi everyone, I'm Joey Lam. I'm working with Amos Tai to develop an ecophysiology module in GeoSchem. So basically, we are replacing the parameterizations of somatal resistance in dry deposition with the new ecophysiology module to do mechanistic simulation. And then we also conduct some simple model experiment to see the model performance. So if you are interested, please stop by poster number 26. Thank you.
Hello everyone, I'm Yang Li. I'm a postdoc at Harvard.
So in our research, we use a coupled vegetation climate model to predict fire activity and smoke concentration under future climate. So following the worst CO2 increasing scenario, we found there is a clear northward shift in living biomass. And also we found there is a northward shift in fire activity and also smoke. Especially our simulation indicate there could be some like a lot of national forests could be under fire danger, including the national Yellowstone National Park. So find out more, come to my poster.
Hi, I'm Regine Dang from Institute of Atmospheric Physics. As we know, the PM2.5 concentrations in China have decreased dramatically in recent years, while those of ozone have increased. So in this study, we look into the related radiative forcing and health impact of aerosols and ozone during the emission control period 2012 to 17 based on the geochem simulation. So if you're interested in our estimates, welcome to my poster B28. Thank you.
Hello, everyone. An understanding of PM2.5 precursor emissions is crucial in developing informed pollution mitigation policies. In this study, we use the geochem adjoint in order to calculate the impact of sectors, species, and regions on the PM2.5 burden in over 100 countries and the city of Washington, D.C. I'd love to chat with you. My name is Omar Nawaz from the University of Colorado, and my poster's at B29. Thank you.
Oh, hi everyone, I'm David. I'm in Amos Science Group, and the poster will contain more of the results that he actually presented. That we have surface ozone, and then we put it in our in-house model called Timir, and then we look at the impact on the vegetation. Yeah, I posted the slides too late, so it's on there. Yeah, but some of the slides are seen already. Thank you.
Hello everyone, I'm Li Zhang from Peking University. My work is to estimate aerosol cloud rainfall interactions with simulations by WolfCam. We find that aerosol cloud radiation effects are much important for the decrease of rainfall and MCS events over southern China in springtime. For more details of the result, welcome to my poster number 31. Thank you.
Hi, I'm Elizabeth Klavinsky from the University of Houston, and right now I have a preliminary comparison of isoprene emissions from online GeoScan Megan 2.1 compared to offline Megan 3. And this work was inspired by the response of BVOC emissions to drought stress. So if you're interested, please come by poster number 32. Thank you.
In 2020, the UN will require ships to emit significantly less sulfur dioxide. This will reduce atmospheric concentrations of sulfate, which will induce a warming effect. One way to reduce this warming effect is to also reduce the emissions of black carbon from ships, something that has not really been done in the past. So we investigate the radiative effects of reducing SO2 and black carbon from ships using GeoSchem, RRTMG, and TOMAS. And my poster is at B33. Thank you.
Thank all the speakers and post-presentation.
Yeah, thank you, Hong. Thank you for keeping all the speakers on time. Thank you for all the speakers. So now we're moving on to working group breakouts. So find your working group on the agenda. We have a chemistry working group meeting here. The chemistry ecosystem climate working group meeting across the street in Maxwell Dworkin 115. And the GeoSchem support team will also have a session on new software and coding developments in GeoSchem. So if you're interested in looking under the hood, they will tell you all about it in Maxwell Dworkin G125, again across the street. And then we will have our poster session, 4:30 to 6:30 with refreshments at our usual location. Thank you very much. Thank you, Hong.